Welcome back, and let's get going. So here we are in chapter 4, and this chapter is all about exponential functions. They look a little bit like power functions, but they definitely respond differently. In chapter 3, we saw that power functions had the form y equals ax to the b. All right. In this chapter, exponential functions are going to be y equals ab to the x. So we flip these two guys around. All right. So one of the ways you have an exponential function is if your independent variable x is in the exponent. Makes a big difference. Okay. Visually, at this point, it makes very little difference, but that's what it looks like. Okay. And of course, when we do exponential regression on the calculator, it'll remind us what form we're doing. Okay, so we've got data about a fish called walleye pike. And so we have the length of the fish compared to its weight. And of course, as the length increases, the weight increases as well. Now notice, the length is increasing by regular increments, 10 centimeters each time. If the weights were increasing by about the same amount each time, whatever that amount would be, then this would be a linear situation, like in chapter 1. Just be basically a straight line. But it's not. It goes up by 0.1, then it goes up by 0.2, then it goes up by 0.4, then it goes up by 0.6. And so basically what's happening here is the y values are just about getting doubled every time. Not quite, okay? 0.6 is not double 0.4, but it's close. And so if you can multiply your y values by approximately the same number each time to get the next one, then that means you have an exponential situation. All right. All right, so what do we got here? Make a graph of the data large enough to include 70 centimeters on the x and 4 kilograms on the y. All righty then. So let's get into that. And this is where I'm gonna, once again, I'm gonna take a, I won't bother taking a picture. Okay. So here, then I'm gonna go here, and all right, so got that. Got that. All righty. And let's see that. Wow, that's not the most level line, but whatever. Okay, so we have length and we have weight. All right. And so, I am going to take a picture because it is kind of a pain because I have to click on and off of stuff. Okay, there. I've got a picture of the data. Now I don't have to go back and forth. Let's see. So, the length needs to get up to 70 centimeters. So I guess I'll just go 0 and then maybe 10, 20, 30, 40, 50, 60, 70. And what a surprise, I've already forgotten the other one. Let's see. And 4 kilograms is how high we want to go. All right. So I'll go 4, and then half of that's 2, and in the middle of there is 3, and in the middle of there is 1. Okay. Cool, cool, cool. So now let's start graphing it, shall we? So the first one is at 20 centimeters and 0.1 kilograms. That is not a lot. Okay, good. So 20 centimeters, 0.1 is like maybe right there. And then 30 centimeters and 0.2 kilograms. And then 40 centimeters and 0.4 kilograms. Okay, and I'm going to pause because my boss is calling. Oh my gosh. Okay, so I don't know if you could tell I just paused the video, but I just sold off my car, got hit in an accident. Oh man, I love that car. Such a good car. And my son comes home from his mission tomorrow, so I'm really feeling kind of emotional. And why is that there? I don't know. Is this it? Yeah, that looks like it. Okay. All right, so I was making this cool picture. All right. So here we go. So I'm pulling out the camera. Okay, so we were on x equals 50 centimeters. So 50 centimeters and oh, poop. I need this. Okay. And it was 0.8 kilograms. So about there. And then 60 centimeters and 1.4 kilograms, maybe about there. Now, the shape of the graph of an exponential function typically is something that it just gets steeper and steeper and steeper as you go along. Okay, like compound interest. Okay, so as you go along, it doesn't stay in a straight line like chapter one. It just gets steeper and steeper and steeper. Or it could be that it does something like this. It could be an exponential function flipped over, and that's fine too. Okay, so that I believe takes care of part A. And dang, I'm discombobulated now. Where am I? Okay. So part B, find the slope between 40 and 50 centimeters. And of course, explain the meaning. Don't mind if I do. Okay, so between 40 and 50, okay, just so I've got room here, I'm gonna come back to this thing. And so we're gonna do it just like we always did in the past. And we're gonna say, all right, so the slope is the difference of the y values divided by the difference of the x values, which will be 0.04. And what the heck does that mean? I don't know. I don't care. I just lost my Honda. Okay. Well, it means that the weight of the walleye pike increases by an average of 0.04 kilograms for every centimeter of length. Between the 40 and 50 centimeter marks. Okay, again, like we've talked about in the past, if it's not linear, if it's not chapter one, then it's going to make a difference where, what interval you're talking about. In this case, we're talking about the interval from 40 to 50 centimeters. So yeah, it definitely makes a difference. So you need to specify that. You need to, or you can think of it this way. Write it in such a way that if somebody walked up and saw this, they wouldn't even need to read the problem. They wouldn't need any other information. This right here would mean something real to them. It wouldn't be like, well, I'm not quite sure what you're getting at. No. This works really well. Okay. So next, part C, find the growth rate between 40 and 50 centimeters, rounded to 3 decimal places. All right, I'm just going to do it on this page, and I'm going to get rid of this stuff here just to tidy it up a little. Okay, so find the growth rate. Now that is something different. And when we talk about the growth rate, that's something we only talk about with exponential functions usually. So when you see growth rate, that lets you know we're talking exponential. Okay. Now, in this chapter, it's not a big deal. You're like, well, every problem is exponential. But on the final exam, it's not going to be the case. Okay. So, little cues like that are nice to know. Okay, so the growth rate between 40 and 50 centimeters. That's actually quite easy to do. So you take the second y value, 0.8, and you're going to divide it by the first y value, 0.4, and that'll give you a 2. And that right there tells you that, let's see, hint, okay, they don't ask us to do anything with it. So this, just saying 2, that'll suffice. But what does it mean? It means that at least between 40 and 50, that the weight is doubling. Okay, that the weight is doubling. And so anyway, so that's what you would do. You just take the second y value, divide it by the first when you were doing growth rate. So for part D, I think, yeah, wait, hint, the months are not consecutive, so you'll need to substitute the numbers you know. Oh, wait, I'm sorry. Okay, yeah, this right here will work if these numbers here are consecutive, which they're not. Crap. Okay, so we actually have to do a little bit of work. Okay, so if it was like 4 and 5, so they were actually consecutive, yeah, then this would work. And the author does go over this in I think one of the examples. So we got to do something just a little bit different. Okay, so for that, I want to go back to the other screen, so I got a little more room. Okay, and so because the x values are not consecutive, we're going to have to use the basic, um, the basic formula for exponential function. Okay. All righty then. Okay, so what the A means, the A is your starting value. Well, we're going from 40 centimeters up to 50 centimeters. Okay, so for this part, our starting value is going to correspond to this first point. Okay, our starting y value, 0.4. So that's what A stands for. You're not going to need to do this process very much, but a little. All right, now we need to figure out what B is. Okay, so in order to figure out B, I'm going to plug in a point for an x and a y coordinate that go together. Okay, so I'm going to use the other point. I'm going to say, oh, okay. So now, if this is our starting value, then the second point is 10 centimeters further down the line. Okay, so so that's what I'm going to plug in. I'm going to say, all right, 10 centimeters later for x, the weight is now 0.8 kilograms. And then I solve for b. And I say, all right, well, let's divide by 0.4. And that'll give us 2 equals b to the 10th. And then at this point, we say, all right, how do I get that 10 away from him? Well, we already learned how to do that. We can just, in the last chapter, we can just raise it to the 1/10th power. Okay. And so those will cancel, and we're going to be left with about 1.07. Okay. And I've already forgotten what the problem was about. So isn't that wonderful? Oh, yeah. Okay, I remember now. So this guy right here, that's going to be our growth factor. Okay. 1.07. And what that means is, it means that every 1 centimeter increase of size on these fish, the weight ends up being 107% of what it was. In other words, a 7% increase. So that's what this guy here means. It means you've got a 7% increase for each single centimeter. Now, if you go up 10 centimeters, yeah, you've got about 100% increase. Okay. The population, you're taking this and then adding that on again. But that's how that works. Okay. I know it's a little tricky, but fortunately, you're not going to be doing too much of this type of problem. Okay, moving on to whatever's next. Okay, so for part D says do it again, but do 50 to 60 centimeters. Okay, I can handle that. Normally I wouldn't bother because I'm like, well, I just did one like that. But this is kind of tricky. So yeah, let's do that. Okay, so going from 50 to 60. Yeah, okay. So we'd say, all right, well, let's start off with our basic function, exponential function template. And we'll say, all right, well, we're starting at 0.8. Our starting value is 0.8 kilograms. And we want to solve for B. And so I'm going to take this other point and plug it in. And I'm going to say, well, 60, that is 10 centimeters later. Okay. And what goes with that guy is 1.4 kilograms. So now I'll divide by 0.8. And all right, and then I need my calculator over here. 1.4 divided by 0.8. Okay, and then that gives me 1.75. And then I'm gonna raise both sides to the 1/10th power. And then what? Let's see, so raise 1/10th. Okay, and then that gives us 1 point. I don't think I rounded the other one off like I was supposed to. 1.058. Okay. And so this answer is smaller than this one. And that makes sense because when we went from 40 to 50, the weight was doubling. Okay, but when we went from 50 to 60 centimeters, the weight did not quite double. Came close, but it didn't quite double. So this one here says, all right, the growth factor between the 50 centimeter and 60 centimeter mark is going to be 1.058, meaning a 5.8% increase for each single centimeter of growth. Okay. All right. So let's see. Boy, this is getting hard to read. I did that. E, add a trend line. Estimate the weight at 70 centimeters. Okay, I'm going to have to do a little erasing here. Just a little. Okay, maybe a lot. Okay. All right, time for that trend line. And I'm going to try to do this as accurately as I can. Okay, that's probably pretty good, I guess. All right. So at 70 centimeters, what's going on? According to my very imperfect graph, at 70 centimeters, we're going to be at about 2.5 kilograms. So, yeah, so that's so that would be my answer for that part. So at 70 centimeters, we're at about 2.5 kilograms. All right, and I think there was one more part. Use your trend line to estimate the length a walleye would have to reach to weigh 4 kilograms. Asumecha. Okay, so let's see, 4 kilograms. Go to a different color now because it's fun. So 4 kilograms is going to be about there. That looks like about almost 80 centimeters down here. I'd say maybe, I don't know, 78 centimeters or so. Again, you're going to make an imperfect graph and then you're going to estimate imperfectly, do your best, but we're not all going to get the same answer. If we all get the same answer, then I know something's fishy. So anyway, that's it for that one.